Continuing our discussion of the development life cycle, one of the phases is testing. So we're going to look at security testing. Our objectives here, we'll talk about static and dynamic analysis techniques, penetration techniques, and some real-world examples of flaws or vulnerabilities that either were discovered through testing or which should have been discovered through testing. So we talk about static analysis, dynamic analysis, and penetration testing as our three primary techniques. And this chart depicts that there is some overlap and some gaps between them. No one of these techniques will find all of the flaws. No one is perfect. And in fact, it's important to understand that one of the limitations of testing is that it will never demonstrate that you have no vulnerabilities. All it can do is find what it finds. But a clean report, a report that says we couldn't find any vulnerabilities, means only that. No vulnerabilities or flaws were found. It does not mean they do not exist. Static analysis is really a security-oriented review of the code. Now this happens normally during development. Programmers review the code as they write it and hopefully produce code with no flaws. As code gets more complex, we have to automate this process in order to deal with the volume of code. Consider a modern operating system that has tens, if not hundreds of millions of lines of source code. This is beyond the scope of human manual review. So we have to use automated tools. Thankfully, these tools exist and are accessible. Let's look at a specific example of something which would have been discovered by static analysis. Examine this function. We're going to test if someone is an administrator by evaluating their permission level. So, if permission is greater than 2, we return true. If permission is less than true, we return false. What happens if permission is equal to 2? That's undefined. So now we have a program, we don't know how it's going to behave in a specific situation. That's not good. This would have been detected through static program analysis. Another real-world example, a little more complex. So examine this code segment and see we're testing if options are equal to wclone or wall, and if the current user ID is equal to 0. And if that statement is true, we return einval. But what's wrong with this code? That is not a test. The double equal is a test. The single equal is an assignment. So in practice, the way this would work, if I test options equal wclone or wall, if either of those are true, then I'll evaluate the other side of the AND statement, the double ampersand. And in this case, I'll assign the current user ID to 0. Now this is C code from the Linux kernel, and the effect of this would be that under the right conditions, you would set the user ID to 0, the root user, an elevation of privilege, a root level exploitation. This was actually discovered in the Linux kernel immediately prior to publication. So if it had been rolled into the production code, a root level elevation of privilege exploit would have been possible. This was discovered through static analysis. Another real example, the Heartbleed vulnerability. Now this is just the vulnerability of the day, if you will. This particular one was published on April the 1st, 2014, under the CVE number listed here. The Common Vulnerability Enumeration Project lists and indexes vulnerabilities so that security professionals can refer to them explicitly and we all know what we're talking about. Again, this particular vulnerability was announced on the 1st of April of 2014. Now that date was particularly poorly chosen because what happens on the 1st of April? April Fool's Day. So many people choose April Fool's Day or the 1st of April to perform practical jokes and to release joke messages or jokes of things of that nature. This particular vulnerability was published on the 1st of April, and not everyone took it seriously immediately because of its publication date. What it does is exploit some poorly written code in a common SSL library called OpenSSL. Let's look in detail exactly what happens. The Heartbleed vulnerability exploits a bug in the optional heartbeat function of SSL. This is an application layer mechanism where the client and server can keep track of each other and determine that both are still alive and operational. The way it works, the client will send a heartbeat message with a payload, in this particular example, the word potato, and the length of that payload, 6 bytes, to the server. The server gets the heartbeat request, writes it into memory, and then reads it back out, 6 bytes, and returns it. Client sends potato, 6 bytes, gets back potato, 6 bytes. Now both sides know the other are operational. So we can do this again. In fact, the heartbeat function operates periodically, just like your heartbeat. So if I send the word bird, 4 characters, it's written into memory, 4 bytes. It's read out of memory, 4 bytes, and sent back. But wait, hackers don't follow the rules. What if the hacker sends a 3-letter word, hat, but tells the server it's 500 characters or 500 bytes long? Hat is written into memory, and the server, when it responds to the heartbeat request, reads 500 bytes and sends them back to the client. This effectively means the client can read all arbitrary memory from the server and disclose everything, compromising keys, sensitive material, user data, everything. Heartbleed existed in OpenSSL from versions 1.01 through 1.01F, and all of these versions are vulnerable. You can test your code to see if it's vulnerable by following this link, but this gets worse. Reverse Heartbleed works in the other direction, and Android phones, the Android operating system, uses the OpenSSL library. So Android version 4.1.1, codenamed Jellybean, is vulnerable, and all previous versions are vulnerable. If your phone supplier or your carrier has not supplied you with an update to your operating system to bring you past 4.1.1, you are vulnerable. About 50 million devices, 50 million devices worldwide are still vulnerable, and you can go today to common retail outlets and still purchase devices new from the factory or the supplier containing vulnerable versions. For the record, iOS, the iPhone, BlackBerry, and the Windows Phone never had this problem because they don't use OpenSSL. Dynamic analysis reviews the code as it's running, not the source code, but the application code running either on its intended platform or within a simulator. And this mimics how an attacker would actually attack the code itself. The attacker doesn't need access to the source code. All he needs is access to the running application. So in the mobile world, that means if your app is in an app store, the attacker can download it and use dynamic analysis techniques to try to find vulnerabilities. These tests can be very, very carefully created or quite random. or accidental. Something as simple as entering something unexpected to the program, which underlies the need to validate input. If you're performing dynamic analysis tests, consider carefully the back end and the production version. These tests can have great impact on running systems, so while you always want to test against the production version, you don't want to test against the version that's in production. Duplicate it, test it offline. An example of a dynamic analysis technique is something called fuzzing. Fuzzing involves using the attack surface analysis technique to determine attack points, inputs and outputs, either physically or over the network, and then supplying random inputs to those input interfaces, hoping to cause an abnormal end or interruption with the program. When the program behaves erratically, I'll reduce my input to find exactly what caused it and then begin modifying it, hopefully to be able to influence the behavior of the program. Much more information on the fuzzing technique is available from OWASP or from IBM, and in fact, the Heartbleed vulnerability was discovered through fuzzing. So a real-world example of a vulnerability that could have been detected or should have been detected through a dynamic analysis technique like fuzzing. Let's look at the USS Yorktown. In the United States Navy in the mid-90s, a decision was made to transition from control of the ship via dedicated, purpose-built military computers to control using commercial operating systems and commodity computers. In this case, Windows NT 4.0 interconnected on the ship via fiber optic network. So in 1997, while on one of its testing cruises, the Yorktown, a crew member entered a 0 into a program field. And this 0 was stored in a database somewhere and later retrieved by another piece of software and used as the dividend in a division operation. If you remember mathematics, division by 0 is not defined or allowed. So the computer involved, the program crashed. The crash cascaded over the fiber optic network to all of the other control systems on the ship, and the ship went dead in the water. Had to be towed back to port. This is an example of a flaw, a program flaw that would easily have been discovered through testing techniques in the dynamic analysis category like fuzzing. Our third technique is called penetration testing. This is where we, as the defender, pay someone to attack our system, to act as if they were a criminal hacker coming after our system. We divide penetration tests into two broad categories, white box and black box. In a white box test, the attacker is given all of the information he could possibly desire, up to and including possibly the source code for the application, so that he has all possible advantages to attempt to attack and subvert our code. In a black box test, the tester is only given the identity of the target. Attack me, attack my program, or attack my systems. And they must research and determine all the information on their own. Penetration tests can discover flaws and vulnerabilities, but where they're really powerful is in demonstrating to your boss, to your manager, that you have a vulnerability that you perhaps are already aware of, but that it can be exploited by an attacker. This can help you generate budget to correct flaws. The weakness of a penetration test is the weakness shared by all testing techniques. The failure to identify a flaw does not mean that a flaw does not exist. So a report from a penetration tester that says no flaws found means simply no flaws found, not that no flaws exist. We talk about hackers, and the industry uses three terms for these guys. We call them black hats, white hats, and gray hats. These refer to the old cowboy western films out of Hollywood back when we were children. And if you remember those, the good fellas always wore white hats and the bad guys always wore black hats. And you could tell who was a good actor or a bad actor, or a good person or a bad person, by the color of their hat. So we refer to hackers as white hats if they are our professional friends and they're helping us try to learn how our systems work, how they can be attacked. And the black hats are the criminals who come after us, attempt to steal our data, and violate our systems. Unfortunately, sometimes there are people who act on both sides of that fence, and we call these fellows gray hats. Sometimes their hat is black, sometimes their hat is gray. The important lesson here is if you hire a firm or an individual to do a penetration test, you want to be extremely diligent to make sure you have a firm or a person with a good track record, a proven reputation, who is ethical, that you can trust to not be a black hat or a gray hat. A real-world penetration test. If you don't hire the hacker, don't worry, he'll come after you. The Target Corporation is a major retailer in the United States and North America. And in December of 2013, it was announced that they had been penetrated and approximately 40 million credit card records were compromised. 40 million. Now consider the cost of replacing a credit card. Mailing out the new card, generating the new card, revoking the old card, dealing with the compromised data, and perhaps the financial loss that goes along with it. So you can see that 40 million credit cards being compromised is a major, major compromise. How did this happen? The attacker exploited a known vulnerability in a Windows operating system which had not been patched. The fallout from this particular exploit: the chief information officer from Target had to resign. The chief information officer, by the way, had no IT experience. And the PCI mandated penetration test, the payment card industry's data security standard, mandates that if you store, handle, or transmit credit card data with an automated system, that system be penetration tested at least once a year. That test had never been performed, and this vulnerability would almost certainly have been discovered if it had. Thank you.